All right, so we're taking our first step in learning target 1, where we're using law of sines and law of cosines to solve triangles. And essentially what's going to happen now is you're no longer going to see right triangles. For example, when I give you example 2, notice that we skipped example 1. That's because I said you do not need to worry about area right now. You will learn about area when you get into pre-calc. Whenever I say solve a triangle, that means I need to solve for all missing components. So when we look at this one, I notice I don't have angle B, I don't have side A, and I also don't have side B. Well, notice that if I have 2 of my angles, it's very easy to find the third because the total sum of the angles should be 180 degrees. So I take the total, and I'm going to subtract 45 degrees, and I'm also going to subtract 55 degrees, getting me measure of angle B is 80 degrees. All right, so I'm actually going to veer away from what the textbook suggests. Notice that we're solving for sides. Whenever I'm solving for a side, or if I'm solving for an angle, I direct the law of sine ratio in the direction that I want it to be. So first, let's solve for side A. The law of sines tells me the side of A over the sine of angle A, which is sine of 45 degrees, is equal to another firm relationship. Well, the other firm relationship I was given was C. Side C is 12 divided by sine of 55. Notice that because I placed A in the numerator, what I was solving for in the numerator, is going to be really easy. All I'm going to do is multiply both sides by sine of 45. So A is going to be 12 times sine of 45 divided by sine of 55 degrees. Now, please be aware, whenever you're typing this expression into your calculator, you do need to be in the degree mode. And when you type in this expression, so long as you are using proper parentheses and proper order of operations, you get that A is approximately 10.4 units, okay? Now, we're going to solve for the other missing component, which was B. Again, because I'm solving for a side, I'm going to place the side on top over the sine of his angle, which was 80. And I'm going to set this again equal to my firm relationship. Notice that I'm not going to use the ratio of A, and the reason I'm not is because we had to round right here. And that's going to cause inaccuracy with my B. So I'm going to multiply both sides by sine of 80, and we get that B is equal to 12 times sine of 80 divided by sine of 55. Once again, watch how you're typing into your calculator, and you get that B is approximately 14.4 units. So here are our solutions. We have A is 10.4, B is 14.4, and angle B is 80 degrees. All right, so we're going to get into some other examples, and notice that you should now have written down the chart explaining when you're going to end up with one answer, when you're going to end up with no answer, and when you're going to end up with actually 2 possible triangles. And I'm actually going to talk you through another logical approach to these, except that's different than the one described in the textbook. So in this problem, we are to solve triangle ABC given an angle A, a side A, and a side B. Because I was given a side B, the first thing I'm going to solve for is the angle B. So I'm going to use the relationship of sine of B over 17 is equal to the sine of 118 degrees divided by 20, because this is the first firm relationship we have. First, I'm going to multiply both sides by 17. So we get sine of angle B is equal to 17 times sine of 118 all over 20. Now I'm going to point this out. Sine of angle B. This expression here approximately is 0.7505. I want you to recognize the fact that on the unit circle, did you ever see a sine value that was bigger than 1? Did you ever see one that was smaller than -1? No, that's because your range of your sine function is actually bounded between 1 and -1. So because this statement is the sine of some angle is 0.75, I know I'm going to have at least one answer. All right, so now I'm going to take the sine inverse of both sides. So B is going to be equal to the sine inverse of 0.7505. This gets me B is equal to approximately 49 degrees. Okay. So if angle B is 49 degrees and angle A is 118 degrees, and the total degrees of a triangle is 180, this tells me that C is approximately 13 degrees. All right, I'm going to zoom out and talk about why this one actually does not have two solutions. All right, so the very first angle that we found was 49 degrees. And notice that the sine of this value, sine of 49 degrees right here at this step, was equal to 0.7505, a positive sine value. Well, positive sine values only occur in the first and the second quadrant. Well, 49 degrees is our first quadrant buddy. Then we need to figure out who is in the second quadrant that would also produce a sine value that is the same as 49 degrees. To do that, we take 180 and we subtract 49 degrees, getting us 131 degrees. So then I ask you, can we have a triangle that has 131 degrees, as well as an angle of 118 degrees, and still have room for another angle? No, that's impossible. That's the other reason why the textbook talks about, because this triangle given is obtuse, we know there's only one scenario or maybe two cases here, okay? We'll return back to this logic in just a moment. Now, the last piece of missing information that we have is, what is side C? We now have his angle, but we need to figure out his side. So once again, I'm going to place C on the numerator over the sine of 13 degrees, and I'm going to set this equal to our firm relationship of 20 over the sine of 118. Notice I keep referring to our firm relationship. It's whatever has both pieces of information firmly given from the get-go. So I'm going to multiply both sides by sine of 13. So we get 20 times sine of 13 divided by sine of 118. And when you type that into your calculator very, very carefully, you get approximately 5.1 units for your value for C. All right, so now we're going to take a look at a scenario, an example 4 that, well, according to the textbook, is going to end up with no solution, but let's talk about why. So I was given an angle A as side A and a side B, which tells me the first thing I'm going to solve for is the sine of angle B in the numerator. It's going to be placed over 9. And we're going to keep that relationship constant. We have sine of 50 degrees over 5. Well, I'm going to multiply both sides by 9. So sine of B is equal to 9 times sine of 50 all over 5. When you type this expression into your calculator, you're going to get 1.37. And if you didn't notice, and if you kept going and you did sine inverse of this quantity, your calculator would all of a sudden kind of go into conniption and it kind of says error. Well, error implies no solution, but here's why. The reason it's no error is because this value here is greater than 1, and like I pointed out before, our sine values are bounded between 1 and -1. All right, so now we're going to take a look at example 5. I am given angle A and side A as well as side B. So I'm going to have to solve for angle B first. So we have sine of angle B over 14 is equal to the sine of 39 over 10. Multiply by 14, so we get sine of B is equal to 14 times sine of 39 all over 10. I'm then going to take the sine inverse of both sides. All right, and so when we do that, that ends up giving our value for B, and so we figure out that angle B is approximately 62 degrees. Okay, so now we need to figure out, can there be a second case? Would it make logical sense? And so like I mentioned, if we have a second case, we're going to check to see what his buddy would be like. Who would produce the exact same sine value as somebody who's in the first quadrant who's 62 degrees away from the x-axis? Well, in the second quadrant, to figure out who's 62 degrees away from the x-axis, we take 180 and we subtract 62 degrees to find 118 degrees would be his buddy angle. They are going to have the same sine value. So now I ask you, 118 and 39, is there room for another angle? Well, 118 and 139 is only a total of 157, so there's still room for another angle. Notice in the previous example, there was definitely not enough room for another angle because both angles were huge. Anytime those two angles produce something more than 180, you know it's not possible. So in our first case, we have B was 62 degrees. And in our second case, we have B is going to be 118 degrees. Now to figure out our value for C in both of them, they're going to be separate. In the first scenario, we have angle A is 39 and angle B is 62, which so far is a total of 101 degrees. Well, we have a total of 180, we take away 101 and we get angle C is 79 degrees. In our third scenario, we had 118 for B and 39 for A. Well, when we add that up and take it away from 180, we get angle C is 23 degrees. Now, the next piece of information that we need to solve for in both of them is side length C. Now, it's going to be different in both of these problems because both of them have a different value for angle C. Now, I'm going to use my firm relationship that was given from the very beginning of my problem, and that's my ratio for A. Multiply both sides by sine of 79, so we have 10 times sine of 79 all over sine of 39. We type this in and we get that C is approximately 15.6. We do the same thing over here, but this time we have to be careful because C has an angle of 23 degrees. So notice how the steps are going to be exactly the same, but the numbers that I'm using are going to be different. Multiply both sides by sine of 23, so we have 10 times sine of 23 all over sine of 39. So we get that side length C is approximately 6.2. So notice all the different components of my solutions for whenever I have two cases. All right, so now we're going to move into our last example for this section, which is a real-world problem. So it's going to take a lot of patience when reading it. A lighthouse is located on a rock a certain distance from a straight shore. Okay, so here's our lighthouse. Okay, and here's going to be our shore. The light revolves counterclockwise, so we're going to go around this way counterclockwise at a steady rate of 1 revolution per minute. As the beam revolves, it strikes on the shore that is it strikes a point that is on the shore that is 2,000 feet from the lighthouse. So all of a sudden I'm rotating and I hit a point on the shore, and this is 2,000 feet away from the shore. 3 seconds later, the light strikes a point, and that's going to be 750 feet further down the shore. So the distance between these 2 points is 750. Okay, whatever the unit rate is. To the nearest foot, how far is the lighthouse from the shore? So the distance that I'm actually trying to figure out is the distance from the lighthouse straight across to the shore. So here is essentially what my problem currently looks like, okay? One of the pieces of information that I was also given was the fact that 3 seconds later, the light strikes a point that is 750 feet further. So I'm actually given this angle of rotation here. Because the lighthouse makes 1 revolution every 60 seconds, because it made 1 every minute, the angle that it revolves is actually 3 seconds long. Okay, which we're essentially looking for 3/60th version of 360 degrees, giving you 18 degrees as this angle of rotation. Because remember, it's 1 revolution per minute, so we rotate a full 360 degrees per minute, and we're trying to figure out how long or how many angles it was for 3 seconds, okay? So currently this is what we have, okay? And this is what we need to find. Well, the first piece of information that we could find is this angle right here, okay? What is this angle? Well, using the information, I have angle 18 and his side is 750, and this angle has a side of 2,000. So if we solve for this angle, let's call him C, and we place him as sine of C over 2,000. That's going to be equal to sine of 18 degrees over his side length of 750. Then it's just like our problems before. I'm going to multiply by 2,000. So sine of c is equal to 2,000 times sine of 18 over 750. Now I'm going to take the sine inverse of both sides. So c is equal to the sine inverse of this giant quantity. And when I take the sine inverse of that giant quantity, I get that it's about 55 degrees. The next piece of information I can really analyze is the big triangle that I have in general. The big triangle that I have in general is a right angle. And we've just figured out that this is 55 degrees here. Well, we can figure out the total amount of this angle, and then we recognize the fact that no matter what, this tiny piece in here is 18. So then we can figure out what the remaining piece is. So our total angle, 180 minus 55 minus 90, gets me an overall angle of 35 degrees. Okay, so the whole thing is 35 degrees, but we already know that that little piece in there was 18 degrees. So this little piece is 18, and so that means this other piece in here is 17 degrees, because the whole angle was 35 degrees. Notice that I'm just continuously redrawing my triangle. After I find pieces of information, I'm just redrawing it, okay? So let's draw it one more time then. Okay, here's my big right triangle. We now have this little angle in here is 55 degrees. This guy in here is 35 degrees. And then we cut it. And we got this is 2,000. And this is 750. Okay? All right, so the goal of what we need to find is this guy right here. Well, this little piece was 17 degrees. So one of the things that you can remember is your geometry. And notice that what we're looking to find is his adjacent, and what we already have is his hypotenuse. Adjacent and hypotenuse refers to cosine. So the cosine of 17 degrees is equal to his adjacent, which is x, over his hypotenuse, which is 2,000. Multiply both sides by 2,000, so we have 2,000 times cosine of 17 degrees is equal to our x, which is a total of 1,913, and I believe we're using the unit of feet. All right, so now we're starting the next section, which is going to feature the law of cosines. So the law of cosines can be used whenever the law of sines initially can't be used. And notice that I say initially, because essentially what's going to happen is you're not going to be given any firm relationships. For example, notice in this problem that I'm given the angle for C and then the side for B and the side for A. There's no firm relationship, okay? So what I'm going to do first here is I'm going to solve for side C using the law of cosines. Well, the law of cosines is C squared equals A squared plus B squared minus 2AB times cosine of angle C. What I'm looking for is, once again, what I'm set equal to. So C squared, and now I just got to plug information in. We have 18 squared for our A. We have 24 for our B, minus 2 times 18 times 24 times cosine of angle 57 degrees. One of my words of wisdom here is to make sure you're being very careful in following order of operations, especially when typing in this long expression here. Notice that these are being multiplied by the cosine of 57, so they can't be combined with anything else. So you simplify that and you get approximately 429.4. So then we take the square root of both sides, so C is equal to 20.7. Now, here on out, your textbook actually recommends using the law of sines, and I do recommend that as well because it's actually a little bit more efficient. So now we're going to be solving first for, let's solve for A. So we have sine of angle A over its side length of 18. We now have a firm relationship, so we have sine of 57 degrees, and his side length, while it is approximate, we're going to use 20.7. multiply both sides by 18, so sine of angle A is equal to 18 times sine of 57 over 20.7. Next, you're going to take the sine inverse of both sides, and when you take the sine inverse of this big, long expression here, you get that angle A is approximately 47 degrees. Now you can use your rules of triangles because you have one angle, two angles, and we need our total to add up to 180 degrees, letting us know that angle B is 76 degrees. All right, so now we're going to look at example 2 where I'm given 3 sides. One of the recommendations is always to solve for the largest angle first whenever doing law of cosines. Well, the largest angle is going to be across from the largest side. So we're going to use our formula here. We're going to have 15 squared is equal to 9 squared plus 7 squared minus 2 times 9 times 7 times cosine of the angle A that I'm looking for here. So I'm going to start to simplify my expression here. What I can do is I can subtract 9 squared from both sides as well as subtract 7 squared from both sides. So I'm starting to isolate my variable, okay? The next thing what we can do is we can divide both sides by this quantity of negative 2 times 9 times 7. And when I do that, we have this expression here. 15 squared minus 9 squared minus 7 squared all over negative 2 times 9 times 7, giving me approximately negative 0.754. I would recommend doing this in your own calculator while I'm talking about it, just to make sure you're remembering how to properly plug things in. So now we're going to take the cosine inverse of both sides, and when I do that, terrible notation, Miss Rudolph, you get 139 degrees is equal to your angle A. Now our first angle is solved for, so we can move on to our next one. Let's start solving for angle B. Once again, I can move into using the law of sines because it's a little bit more efficient. And remember, sine of the angle over its side length. And now I have a firm relationship with A. So I'm just going to multiply both sides by 9, so the sine of angle B is equal to 9 times the sine of 139 all over 15. Last thing I must do is take the sine inverse of both sides. So B is equal to the sine inverse of that entire quantity, which is approximately 23 degrees. Well, now we have angle A is 139, angle B is 23. If we add those up and take them away from 180, that implies that angle C must be approximately 18 degrees. All right, please notice that you're given a chart to fill out, and I highly recommend filling it out. In fact, I require that you fill it out because it'll get you thinking about when to use which law. All right, in example 3, you're given a real-world scenario, and in fact, you're even given an image that already sets up the situation where it looks like that we have a medical rescue helicopter flying to the scene of an accident, and then it's going to need to fly to the hospital to take care of its patients. And it says, how far is the hospital from the base, which is why we're looking for this A here. And so we're going to use law of cosines because we have no firm relationship provided. Okay, so we then have 50 squared plus 45 squared minus 2 times this side and that side multiplied by the cosine of our angle 130 degrees. All right, so then we're going to start to simplify this expression here. And when you start to do that and plug things in, you're going to get 7,417.5. Then you're going to take the square root of both sides. You get that A is approximately 86.1. And it looks like we are in, miles. And so what the conclusion that you would draw is that the helicopter landing base is 86.1 miles away from the hospital, which is actually pretty far away.